Good evening, ladies and gentlemen, and welcome to the SAIEE KwaZulu-Natal Centre webinar on data centers, coherent optical technology, and future energy requirements. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Attendees can ask questions via the questions panel located within the GoToWebinar control panel. And by default, the control panel is located on the right-hand side of your screen. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV, under the KZN Centre playlist. This channel is updated regularly, so ensure you check back as often as possible for new uploads. You can find a registration link in the chat box. Please click on it and register. It's free. A certificate of attendance will be issued a few days after this webinar. I'd like to introduce you now to our host tonight, Ms. Crystal Nagisha, who is employed by eThekwini Electricity MV/LV Operations as a chief engineer and has served the organization for the past 13 years, with her involvement in various distribution automation projects and smart grid initiatives. Crystal holds a BSc Electronic Engineering degree from the University of KwaZulu-Natal and graduated with a Masters of Business Administration degree from the University of Pretoria's Gordon Institute of Business Science. She's registered as a professional engineer with the Engineering Council of South Africa and an active member of SEAGRAE, serving on the SEAGRAE SA Women in Energy Net Zero Initiative Work Group dealing with climate change impacts on the energy sector. Over to you, Crystal.
Thank you, Mengs, and good afternoon to all attendees. This evening, I'm very pleased to introduce to you a very esteemed guest speaker, Dr. Muyiwa Balogun. Dr. Muyiwa has conducted extensive research on the topic under discussion this afternoon, and he has obtained a PhD from the University of the Witwatersrand South African University, a master's degree from the University of KwaZulu-Natal, and a diploma in project management from the University College Dublin in Ireland, and a bachelor's degree in electrical engineering from the University of Ilorin in Nigeria. Dr. Muyiwa is an optical systems application engineer. A very warm welcome to you, Doctor. I'd like to now hand over to you.
Thank you very much for the introduction, and also thank you for having me. It's a great pleasure to be among you and also to have this discussion today. And I hope every one of us were able to, at the end of this conversation or talk, to benefit and also to challenge ourselves, more importantly, to do more, especially as far as Africa is concerned. Yeah, so from the introduction, so I think that's just a bit about what I can also say about myself, my educational background. So now going straight to the topic. So we have before us data centers, coherent optical technology, and future energy requirements. So actually putting it just based on coherent optical technology, some kind of narrowing it down. So I think it's actually broader if I just talk generally about optical technology, because it's a pretty broad technology. So and each of those that we have in this topic, from data centers to optical technologies to energy requirement, these are distinct topics on their own, and we can talk about this the whole day, but we just see how we can actually weave all of this together to have a proper sense of direction, either where we have our future directions. So for the agenda today, we look at a brief history for those who are not very conversant with these data centers that we're talking about. We look at a brief history. Then we look at the energy we look at the architecture first, and then we look at energy requirements briefly. Then we look at the communications and data processing aspect of data centers. And then we look at the challenges we have, energy challenges, and even some other challenges that we face today. Now, let's go to the brief history. So today, if you look at any business, doesn't really matter the kind of business, you're going to need some kind of computing equipment, some kind of computing facility, maybe to process your infrastructure, to process your applications, maybe internal applications from HR to accounts, IT operations, offering services even to customers. And then these are very important today where you need your IT equipment to get all of these things done. But as the business expands, you realize that you need to increase the IT facility, and then you need to get them in a particular room so that you can have some kind of control. So that's actually where the rationale behind this data center that we're talking about came from. So you want to have this benefits. Number one, you want to prevent your equipment from experiencing power outages. You want to prevent against power outages. Number two, you want to have a very quick replication. You want to have a possibility of having quick replication of your data in case of disaster recovery. And also you want to have your equipment in a controlled room, temperature controlled room, because if you keep your equipment in such environmental facilities, they actually prolong the lifespan of your equipment. And then you want to be able to quickly roll out some compliance mechanism in these days of GDPR. You want to have your facilities protected from also some security breach and all of that. So you're able to do all of this very quickly when you have a dedicated space where you have your IT equipment. That's actually what's give rise in the first place to what we know today as data centers. So we can back up a little bit and then look at the beginning when it first emerged. So data centers actually emerged first when you have some military operations going on, and then they needed to do some computing operations. So that gave birth to what we call the ENIAC in 1945, housed at the University of Pennsylvania. If you look at the bottom left corner here, you see a picture here of a man inside that building. So at the time we have, that's thanks to the University of Pennsylvania here. So at the time we have very big components which operators, they need to connect with several cables, several wires. And then at the time it made sense actually to put them in a particular room so that we have some kind of control. Also, these things they were radiating lots of heat and all, and some other issues like this, like the cabling and all of that. So you need to bring them in a particular room so that you can have more control. So that's actually when we have the pseudo data centers, where you have this huge computer in a room, several cables, several components, huge connected together, and then you have a huge cooling facility as well, so that you can have better control. So by the 1960s to 1970s, then that's actually when we had the birth of the transistorized computers called the transistor digital computer. This is actually like a big deal. This is a big revolution at the time where we had transistors in the computers, and then that was what gave birth to the Moore's law in 1965, where he predicted in his paper that we're going to have the doubling of transistors over the next 10 years on integrated circuits, and this was actually found to be true. So since that time, the goal has been to see how we can reduce the size of computers, to see how we can reduce the amount of power that computers consume. The goal has been how we can also put in place a proper system like cooling system, so we don't have like computers producing lots of heat, all right? So by the 1980s, 1990s, we've had that was actually where we had the advent of the personal computers, and that's actually when we had the true data centers. So these are the kind of server rooms I first experienced. So when I was actually doing my internship back in the days, we used to have this server room at the time. So that's actually where we put all of our facilities. We put our computers, the mail servers, and all of this, so that we can actually manage the going ins and out of the organization in terms of the data, and also mails and all of that, the database as well. So that's actually when we had a real so-called data center. At the time, we normally call them like server rooms, right? So, but come 2000, and then between 2000 and 2010, there was actually, thanks to some kind of innovation at the time, we had this great innovation in network technology, so that we are able to operate applications on remote hardware. The hardware, they don't have to be right on the premises. They can be remotely somewhere, and then from those hardwares, you can actually run your application. And based on those technologies, we had the AWS offering computing, storage, and IT infrastructure in 2006. And that was actually like a huge evolution at the time. And then that gave birth to what we have today, where we're talking about hyperscale data centers, we're talking about DCIs. This is actually the data center interconnect that we have today. So, and also this data center, they actually depend on the kind of business that you operate, right? So we have different tiers. We have tier 1, we have tier 2, we have tier 3, we have 4. For tier 1, this actually, they have the basic capacity level to support IT systems for an office setting, right? Where you have your UPS, you have your physical area for IT systems, you have your dedicated backup generators, you have the cooling systems, and then they actually allowed an annual downtime of about 29 hours, right? So they can be down maybe for some kind of operations, or to do some kind of quick work. Maybe there's some kind of servers there that they need to be repaired or to be maintained. Then you are allowed to have downtime of up to 29 hours. Then we have the tier 2, where you have the opportunity to get in more cooling components, where you're able to achieve or to get a downtime of about 22 hours a year. So that's actually like some kind of upgrade from the tier 1 data centers. Then we have the tier 3, where you have lots of redundancy in the facility, where you are able to maintain or replace equipment without system shutdown. You can only have a downtime in this kind of facility for just 1.6 hours in an entire year. This is actually like a huge improvement. Again, it depends on the kind of operation or organization that you run. Then you have the best tier possible, which is the tier 4, where you only have a downtime of 26 minutes each year. Here, when designing, you have to plan for a lot of things. You have to plan for unavoidable disruptions, like, okay, some things that you can't even foresee, both planned and unplanned events that you do not know. You have to put all of these things into consideration when you're building, when you're designing this type of data center. So depending on your business, you can actually select from all of these, and depending on the priority that you're dealing with when you're talking about your own operations. Now, these data centers that we're talking about, we have more than 10,000 data centers worldwide today. And a chunk of those data centers, you have them in the United States, over 5,000. And this figure that you have here, it's actually from September 2023, which is actually about a year ago. So since that time, just this year alone, there's been like lots of data centers coming up and aggressive building of new facilities everywhere across the world, right? So you have the US standing at above 5,000 data centers, and then you have Germany at 522, and then you have China at 448, which is actually currently more than that. And it's pretty tricky, because when you look at the numbers, you might think, oh, China with the population and how they've actually made like huge strides in in communications generally in recent years, they should have more than that. So, but the issue here is you have different types of data centers in terms of the sizes. So China, they're focusing more on hyperscale data centers. They're actually building like huge data centers, like the one I have here, which is at the top left corner of my screen here. I don't know which side is going to fall on your screen, but I can see on the left-hand side of my screen here, the top left. Let me just change to this pointer. So this is actually like a mega east-west data center, which is going to house about 2.1 billion racks, which is actually really, really huge. It spans lots of square feet. It's actually like a really, really huge facility. It's going to be completed sometime next year. And then this is actually how big data centers can be. And currently, we're just having more and more and more of these facilities being built across the world. But you can see here we have India, we have Poland, and this is actually like the top the top places around the world where you have these connections. So definitely there is no country in Africa here. We don't even have Africa as a continent here. So the whole of Africa, we just have, if we combine the data centers that we have across board currently, it's just around 160 data centers, which the Silicon Valley here, which is actually the third largest state here, where we have the highest, where we have the data centers. After Virginia, we have Texas, and then we have the Silicon Valley that houses that actually has about 168 data centers, and this is actually like more than the whole of data centers that we have in Africa. And then this data center that you have in the Silicon Valley, for example, they consume about 700 megawatts, more than 700 megawatts, just in the Silicon Valley alone. And like I mentioned earlier, I talked about the hyperscale data centers, and then we've seen the advent of hyperscale data centers. It's just rising in recent years, from 2017 to 2023. We can see now we have actually currently we have more than 1,000 data center hyperscale data centers across the globe, and then the US still has a chunk of this, 51%. And the interesting thing is that out of the data centers that we have in the US here, more than half of those data centers are actually located in just one state, in the state of Virginia. And talking about the end users, who are those people who are the main end users when it comes to data centers? We're talking about the financial institutes, the BFSIs, and then we have the IT and telecommunications industry, we have the government, and from the pie chart that I have here, we have about 38% of these end users coming from IT and telecommunications. So it used to not be like this. So previously, it was actually the financial institutions where they needed to back up their database, very important to their operation. But in recent years, we see lots of IT and telecommunications giants just going into this market. And then we have more use as well. Lots of organizations out there, they need to generate more data, they need to store more data, and then we have grown massive users also around the world. So that's actually why it's flipped over, and then we have about 38% coming from this sector alone, and then we have the financial coming second at 26%, and then we have the government, the energy utilities, and then talking about those who are the biggest investors who are actually investing heavily in this market. We have Amazon, we have Google, we have Meta, which is actually Facebook, we have Microsoft, we have Oracle, and then we can see this interesting trend from 2017, how they actually invest in their annual investment growth, right? And then as we got to 2020, we saw this huge leap, especially from Amazon, where they started to put in more annual investment growth of which is actually massive. I think double the amount you have with others, right? And then they still maintain the lead today, but we still have Google there as well. Google might be a little bit tricky because from what you see, it might seem that maybe they're not putting much of their investment in this, but I think they are actually diversifying and also investing in some other companies that can actually help to improve the data centers that we have today. And then we have Meta, and then Oracle here. That's actually they have the list of the investments that we have here. And then we can see the revenue. This is actually important from the African perspective, where we're talking about continent where we're always talking about revenue, talking about money, talking about how we can be more viable, how we can be more independent. So we can see how proper investment can actually lead to great revenues, right? So you see countries that are investing in this. This is just revenues from hyperscale data centers. The market size that we have currently from 2022, we have $80 billion, and then we've seen a steady growth this year. It's actually currently more than 130 billion projected here, and then it's just going to increase exponentially down the years, in a couple of years. Here it's been projected that it's going to be around 900 billion, but definitely we can't tell if it's even going to exit this. So that's actually where we are today when it comes to data center, the market, and also those who are the major players, those who are putting in lots of investment into this endeavor, or what I call it, franchise. Now let's look at data centers. Let's talk about the basic architecture. For those who are not familiar with this topic, for those who are maybe probably hearing data centers for the first time, so data centers are basically facilities where you put your digital infrastructure, where you put your data, where you actually store all of this, and also the facility is equipped with other equipment. You have your uninterrupted power supply in place, you have the backup generator in place, you have a space for your IT, you have an expanded area where you actually put your IT equipment. So in the basic architecture of a data center network, several nodes they need to be connected together. So if you look at the figure that I have here, or the diagram, we have the rack, we have the servers being connected, then we have the racks, and then we have the switches up to data campuses. So each of these, they actually require different solutions, from 500 from 50 to 100 gig to 100 gig. When I talk about this, I'm talking about the data rate. This is actually like, for example, 200 gigabits per second. This is actually the amount of data, amount of bit that can be transmitted per second, right? So that's actually the standard, and we can see from these arrows here, we have one going up and the other one coming down. So these ones, like I mentioned, they require different solutions, and then they also, you put in consideration the link length. As you're moving higher, the distance of the link length, and then you're experiencing for sure some higher amount that you need to pay for your solution. So for example, you have several connections. So you have several connections here, which is actually around 100 meters. So you require several connections when it comes to servers. You have servers, maybe in a particular data center, you have about 200,000 servers, for example, and then you need to connect this. So when you're talking about places where you need to put in lots of connection, then it makes sense for you to look at cheaper solutions that they're not too expensive, they are cost effective as well. So we have the speed as well, which is actually not as much as when you're now looking at a link length, for example, of maybe 4 kilometers. That's intracampus. Intracampus means when you have a particular place and then you have different physical buildings which are data centers, and then they are all connected together just in a particular place in a campus setting, so to say. And then if you move up a little bit, then you're talking about the DCIs, which is actually like getting more and more popularity these days, which is actually the data center interconnect, where you are able, the simplest of this is for you to connect point to point. For example, maybe you want to connect from one geographical region to the other. For example, from one local place, maybe from one state to the other. And that's an example. Then you need to connect the data centers together. Then you can do the point to point. And then you have the multi-point as well, where you connect data centers in the network fashion. And then we now have even higher than that, we have the global inter-DCs, where, for example, you have one data center in the US here, and then you have another one, say, in Africa, and then you want to connect these, or for example, another in Europe. You want to connect these data centers together. Then you're talking about link lengths of thousands of kilometers. So, of course, this one also requires different technology. That's actually where technology like coherent optical technology comes to play, where it's actually suitable for longer transmission, and also you can achieve higher bit rates. You can achieve higher transmission, when you faster transmission as well, when you move towards this technology. And then we're still going to look at that even more as we go through this this talk. Now, we've been talking about data centers, and then one thing that's very important when it comes to data centers is actually the energy. So energy is just the backbone of data centers. Without without energy, there is no data center, right? So we need to put proper infrastructure in place so that we can actually run these data centers that we're talking about. So typically data centers, servers alone that we have, the IT equipment alone, they consume about 50 to 70% of the power that's needed in any data center. So we can see from this next slide here, I have this pie chart here where you have the servers showing the storage drives, and then the network. They all contain the whole amount, more than 50% of the power that's actually needed in a data center. So the cooling and power for some other provisions in the system, they only account for 43%. So you can see that these servers, this network, and storage drives or devices, they actually consume lots of power. And then data centers, like I mentioned earlier, you have different sizes. You have the small size data center, you have the medium, you have the large. And then for a typical small data center that has maybe a maximum of, let's say, 2,000 servers, and then you have power capacity, it actually is going to be consuming about 5 megawatts of power. And then we see the large ones are a number of countries, especially the more advanced countries, they are moving towards today, like China, like the US, even Europe. They're moving to hyperscale, where you have buildings, physical facilities of more than 100,000 square feet running to millions of square feet. And then you have, in this kind of hyperscale data centers, we're talking about servers that are like maybe 50,000 servers, more than 100,000 servers, and then they consume lots of power as well. So power requirements vary depending on the size of the data center that we're looking at, the capacity, the design, and some other factors that you need to look into. Those are the things that we determine the amount of power that you need in any particular data center. And data centers, like I mentioned, the energy, power is actually the backbone. So because of this, there are things that need to be put in place to ensure that there is no potential outage, there is no power outage. So you can see from this figure that I decided to put here, from utility feed, you see to the transformer, to the UPS, and then to the power whips, and then to the IT equipment. So the power distribution is designed in such a way as to avoid power outage. And then when it comes to data centers, generally when you design it, you look into two categories of power. You're looking at of power consumption. You're looking at the utility power, and then you're looking at the IT power. The utility power also contains the IT equipment power consumption as well. And then you need to account for IT power separately, so that you're able to understand how much of data just this IT equipment they need, so that you can make adequate provision. So, but all in all, what we're saying here is that you need a very stable and constant power supply, which is actually some kind of problem for example, in Africa, where we have some states where or some countries where it's a huge problem, the power outage problem. So that's actually why we don't have lots of data centers in Africa, because we need lots of we need a huge or better infrastructure, for example. And this is actually how these things are actually put into perspective. So today we have the data centers, like I mentioned. We have them growing or springing up everywhere, different places. You have your data center, especially places like the US, where they've been building lots of data center, hosting different organizations across the globe. But as we have this coming up, then we have challenges. We have different challenges confronting them. For example, we have the bandwidth problem, where you have lots of applications coming up today. These applications, they are bandwidth hungry. You have more users coming into play as well. We have rising energy costs as well. And then we have the land and environmental challenges. Where this actually comes to play is actually the kind of resources that can go into data centers. For example, the cooling aspect of it, it consumes lots of water, for example, in terms of consumption. And then looking at the environmental factor as well, where you're talking about hundreds or millions of square feet being adopted for data center to store servers and all of that. So these actually is causing some kind of disruption. So of course, I am aware that you have some kind of policies in place, you have some kind of regulations in place that actually govern the building of or the design of these facilities. And then we have this challenge of artificial intelligence, machine learning. It's actually like the wave of the moment now. Everyone is talking, or everyone is quickly like on the alert when they hear anything called artificial intelligence. But you need to understand that when you're dealing with these technologies, then it has to do with some kind. It's based on some other factors. So it's actually it's causing some other problems, albeit, let's say, a very welcome problem where we just need to find solution. So with these challenges, we have opportunities arising as well. For example, even in the optical communications domain, we have this problem where we have this channel limit, and then when we're transmitting long distance, there is a non-linearity problem. So we have lots of research going on right now to see how we can overcome non-linearity, for example, in optical communications. And then we see different solutions coming in as well, in terms of cooling, in terms of developing equipment that actually they are low power consuming. So the question now comes to us: how do we deal with these opportunities or these challenges, and also the opportunities as well? So my field, or my specialty, as I mentioned in the beginning, is actually in the optical communications domain, or communications domain generally. I've been privileged to work on the wireless domain and also in the optical domain. So there are a number of things that we need to put in place to see how we can improve this system. So, so I'm going to start with the optical communications domain. So let me just go to this slide and just listen. Yes. So when we come to communications, the optical communications, and also data processing as the challenges and the opportunities. So like I mentioned earlier, we have faster speed, we have greater densities and spectral efficiency rather, which are needed to work properly so that we can have like access to artificial intelligence, machine learning, and all of that. So how can we go about this? So we're talking about improving data rate and the amount of data we can transmit per second. So in this case, we can do that using different methods. So one of the methods that we can use is actually to bring in the parallelization technology, where we can actually have multi-level modulation format, and then we have the opportunity as well, or the option to increase the bit rate as well. So when it comes to bit rate increment, then there are different technologies or different ways by which we can go about this. And then modulation format as well. We can improve the modulation format for, or increase the order of modulation for those who are telecommunications expert in this talk today. So the common modulation format actually include like OOK, for example, pulse amplitude modulation. We have the quadrature amplitude modulation as well. So for the on and off key, we're talking about the modulation format where we're transmitting just 1 bit per symbol. Where we transmit 1 bit per symbol, and then we talk about the pulse amplitude modulation where you're dealing with 4 amplitude levels. So you can transmit 2 bits per symbol on each of the levels that we have. And then we have the quadrature amplitude modulation format where you can increase the bit rate by just increasing the number of bits. So in this particular case, you're transmitting about 4 bits per second. You're transmitting 4 bits per symbol. So for every symbol that you transmit, you're transmitting like 4 bits. So all these, they actually become very complicated very quickly from the telecommunications perspective. So I have, just before we move from here, I have these pictures or the figures that I have here. So from this place here, we have the first one I mentioned, the on-off keying, which is actually the OOK, where you have a high diagram that is properly opened. For those who are, again, not familiar with this, I apologize for the noise there. For those who are not familiar with this kind of diagram, we're talking about when you're transmitting bits and then you have those bits overlaid. This is just like a pointer for you to understand the performance of the signals that you've transmitted. So more often than not, when you transmit, for example, 0, you might get to the at the transmitter, you might get to the receiver, and then you have maybe 1 there. When you transmit 1 at the transmitter, you get to the receiver, and then you detect maybe 0. And then you have some spreading as well as you transmit from one point to the other. So these actually affect the ones or the zeros that you've transmitted, so that the waveforms, they actually spread, and then you can see how they do when you look at the high diagram. When you overlay them on each other, you see that it's not properly opened. So that actually gives you some kind of pointer as to whether your system is actually performing well or not. And then you have the pulse amplitude modulation, which is actually what we have in the middle here. Again, you have the high diagram where you're able to see through about 3 of those. You have 3 eye openings, and then you have the coherent optical technology, which I mentioned earlier. And in this case, where you are able to transmit 4 bits per symbol, and each of these constellation points, so these represent constellation points. So each of those ones here represent, for example, 0, 0, 0, and then 0, 0, 1, and all of that. So with that, you're able to scale up when it comes to your organization. You want to transmit more bit per second and all of that. So when we talk, let's back up a little bit. When you talk about these solutions, when I got here, I realized that it's actually become like a little bit complex, a little bit complicated when we're talking about the solutions. So typically in this space, it's very common for people to deploy software because the equipment that we're talking about here is actually very expensive. So we need to plan properly, we need to design properly, then we need to bring in lots of considerations before we can do an eventual rollout. So when it comes to this kind of endeavors, we bring in lots of software where we're able to simulate our the solutions that we're proposing. We want to simulate the system. We want to see how the network is going to perform in real life situations where we bring in different factors. We consider different factors. We bring these things into play, and then we see how they work. We see how they perform. We see how they respond. Then after that, then we can start investing in the very expensive equipment, and then we do the eventual rollout. So in this case, that's actually why a lot of people, they resort to software where you can see what's going on before you roll these things out. So one of such software is actually the VPI Photonics Design Suite. This is actually the company where I work for, where we are able to offer robust services where you're able to simulate your system. You're able to simulate a lot of this, and you see how they perform. So you also can go from different levels of abstraction. So for example, you are in the organization where you want to design a specific optical amplifier, for example, that is actually going to work in a particular way, or you want to do your design and then you keep your intellectual property, for example. You can actually design that from the components level, and then you scale up. You come to the systems level, and then you see how this component that you've designed, how it's going to work in a bigger system. So in this case here, I have before us a typical simulation that demonstrates, for example, a schematic, which is actually based on the 800 gig pluggable MSA technical specification. So we have different regulatory and technical bodies here where they always come to together so that we can have some level of interoperability within the space. So we have bodies like ITU, we have IEEE standards, we have MSAs and all of this. We have OIF as well. So here is actually based on such standard, which is actually the MSA technical specification standard. This is a PAM4, like I described to you earlier, the PAM4, where you are able to transmit 2 bits per symbol. And then in this case here, we're looking at transmission where the link length is about 2 kilometers. So this is actually very useful when we're talking about just intra-campus data centers, where you have data center within a particular region, and then they need to be connected together within a distance of maybe about 2 kilometers or 2,000 meters, right? And then you need some level of speed. So this is actually where we're heading towards. This is like a futuristic planning, for example, because most of the data centers that we have today, they're actually working on 200 gig, and we've seen in recent times number of these data centers migrating to 400 gig, and then the next is actually going to be 800 gig and above. So we have such planning here, for example, where you have your software and then you're able to analyze it. So in this case now you have like 4 channels here. These are PAM4 generators, and then when you have the signals being generated, and then you use the WDM system, which is actually the wavelength division multiplexing, where you are able to transmit signal a number of signals with different wavelengths. So this is actually a widely used technology, for example, where you do the multiplexing. Then after that, then you transmit through the optical channel. After you've done that, then you want to extract. Typically, when you're analyzing, when you trying to find out how your system is going to perform, in most cases, you just extract one of these channels, and then see how they perform. Then you do the detection here. Here you use a typical photodiode where you can bring in realistic parameters. You can look at the responsivity, you can look at the thermal noise, you can look at the shock noise and all of that. So this module here actually essentially changes from optical domain to electrical domain, and then you do some filtering here. And then what's going on at the receiver here is we're trying to compare the performance of this schematic where we use the 4-error decoder, and then where you don't have the decoder. So these are actually ways by which you can analyze, and then you have the BTR rate analysis as well to show the performance of the system, the number of errors that you have. So the software also comes, for example, with some kind of analysis. So you can analyze your performance. You can analyze that and see, okay, how does this perform? So for example, we transmitted 4 channels, and then you can see these channels here, 1, 2, 3 for each space, 20 nanometers, and then this is the test channel, and then we see the BTR rate performance when you have the 4-error correction and where you don't have it. So you have the good performance where the BTR rate is below the threshold of 1E3, and so this is actually how you can analyze. These are good examples of how you can analyze your system when you're seeking solution to, okay, for example, you have a data center, you want to increase the number of the amount of data you're transmitting per second, you want to increase the speed and all of that. So when we come to the situations where, for example, we want to transmit longer distance or want to transmit at a higher bit rate, for example, that's actually where you have to seek more, or you have to seek a better solution, for example, like the coherent optical technology. So that's actually where a lot of companies are actually tilting towards these days. So this is actually a typical example, and this actually, I love this example specifically because it actually shows you how you can scale your business. For example, you have this OIF standard schematic here, which is based on optical technology, for example. And then maybe, for example, you're transmitting at 400 gig, and then you have a transmission distance like the previous example I showed to you at 2 kilometers. And then as an organization, you built another data center, maybe in another state, in another region, which actually spans 80 kilometers, for example. And then how do you, first of all, ensure fast data rate? How do you ensure that you overcome some kind of impairments along the way? How do you ensure that you can scale up in the future? So this is actually a typical example. So I'll tell you how. So when I talk about improvement in how you can deal with these challenges of data center, I talk about increase in bitrate, and you can increase the bitrate using different methods. Number one, you can increase the bitrate by increasing the symbol rate. You can also do that by increasing the number of channels that you have. So in this case, you have about 3 channels. You can increase the number of channels, and then you can increase the number of bits per symbol. So when you increase the number of bits per symbol, you're operating at a higher modulation format, and then you have an expanded constellation size. So for example, here we have on the transmitter side, we have this Galaxy here, which is actually equipped with dual polarization pump transmitter, and also the Maxenda modulator here. And then when you transmit, for example, you're transmitting at 50 gigabaud. So when you transmit at 50 gigabaud symbol rate, so that means for each of these channels, when we, this is a 16-QAM schematic, by the way. So for each of this channel, that means for the bit rate, you're talking about 50 gigabaud times 4, which is actually 200 gig. That's how you can scale. And then again, in this schematic, we're dealing with dual polarization. Like I mentioned earlier, those are the kind of opportunities that you can explore in coherent optical technology. So you have dual polarization in this case. So for each of this channel, again, apart from 200 that you having dual polarization, that means times 2. So each channel, you're transmitting 400 gigs per second, right? So when you have 400 Gbps here and you're transmitting 3 channels already, so that's 400 times 3. You can see how you can quickly scale up to the terabits region. And then again, you use some multiplexing here, you couple everything together, and then you transmit, and then you have the optical amplifiers here where you set the power limit, the power level. Here for this schematic is actually set at 13 dBm, and then you propagate. And then when you get to the receiver here, inside the receiver, of course, you have the photodiode, and then you have the ADC, which actually helps us to couple all of these DSPs. This is actually one of the reasons why coherent optical technology was actually difficult to handle back in the days, because you don't have all of these technologies in place. But now with the advent of these DSPs that come with reasonable amount of money to pay in, then you are able to get all of these DSPs with different algorithms. For example, this cascade that you have here, you're talking about the DSP, the first one compensating for chromatic dispersion along this fiber link. You have the second one, which is actually the Stokes space rotation. That's actually the compensating for fiber birefringence. And then you have the equalization going on here, and then you have the decimation. And then I don't want to go into the details for some of us who are not too conversant with this kind of systems. So this is actually just a typical way. And then again, you have the analyzer where you can actually see the performance of your system. You have good constellation here. You have the performance where in this case, the concatenated forward error correction was used to. You have the performance below the fake threshold. And so this is just showing you that you need this kind of software for example, for you to scale. These are actually what those big players outside are using to scale, to analyze, to investigate, to even talk about the futuristic performance of their system. So those are the kind of opportunities that we have. So we're able to solve all of these challenges that we have. So another aspect to this is actually the use of the graphics processing unit. So we have this becoming more and more popular these days. And these GPUs are actually just computer processors comprising many smaller and more specialized cores. So they typically used in the AI domain. Maybe, for example, want to run some tests, want to do some trainings and all of that. So the GPUs, they actually come handy in this kind of cases. So you have GPUs gaining more popularity within data centers today, and you have the speed because they can actually increase the speed of processing that we need in today's technology. So talking about the GPU market, we can see how important this market is as they're beginning to gain more popularity in recent times. So we can see from this left side, the upper left here, we see in 2023 where you have about 13 billion being put in, and then 2024 we have 16 billion as the size of the market, which is currently more than this, by the way, and it's been projected as this is just going to be bigger and bigger in the coming years. And then the players that we have NVIDIA. Those of us who follow technology very closely, I'm sure you would have seen in recent times NVIDIA has been the darling of a lot of people, how their stocks have been going up, how they've been doing very well. So you have NVIDIA, you have Alphabet, which is actually the parent company of Google, and then you have the Broadcom, you have all of these players in this market. And these GPUs that we're talking about, they still have they have their own challenges as well. They are still very expensive, and they generate lots of heat actually. So power and cooling they remain a big problem in this regard. And then we have more and more research going on in this space where some companies are already moving towards tensor processing unit TPUs, where you are able to even gain more, where you're able to get faster speed when you're dealing with this machine learning or artificial intelligence-based applications. Now, the energy issues that we confronted with today, we can see this diagram that I have here brings that to a good perspective. So data centers that we have currently, as of this is actually far back as 2020. This is about 4 years now. So when it comes to technology, I can actually say far back because a lot of things are happening like very quickly, right? And then we can see at the time, 2020, we have data centers that we have across the globe consuming about 250 terawatt hour, right? And then today, we even currently in 2024, they're actually consuming more than 450 terawatt hour. And then we have countries looking at the power electricity consumption, which is actually way less than the whole of the data centers that we have. For example, we have Nigeria, we have Argentina, maybe consuming 124, which is way lower than what data centers are actually consuming. And currently at that 450 terawatt hour that they're consuming, that's actually equivalent to the entire consumption of the whole of France. So that's actually how much of a power this is actually needed that they actually consume. And then we have the projection as well. So this is a little bit later. This is actually from 2016, 2017, but most of the statistics that we have out there, they're actually based on this particular paper that we have here. So we can see how they've actually projected that we can only have like more and more consumption of power when it comes to data centers in the coming years. So looking at we're coming very close to the end now. So looking at the global production right now, we see how a lot of countries, they've been aggressively pumping lots of money and doing lots of research so that they can get more energy, right? So we see China, as of 2021, we see their total electricity production standing at below 9,000 terawatt hour, which is actually the highest in the world, followed by United States, but China, it's understandable how they slanting towards higher technology, and then you have a higher population that you're dealing with as well. And then you have the whole of Africa generating below 1,000 terawatt hour, which is actually even which is below what Japan is actually producing. And then when we just put the beam light more into this kind of production, we can actually just zero in on Africa, and then we see the countries that are actually performing, let's say, slightly better than others. For example, we have South Africa leading the way when it comes to electricity production. So this is actually directly related to the data centers that we have. So it's not a coincidence, right, that you have the highest number of data centers in Africa. In South Africa currently, when it comes to Africa, we have problem of data, and then how we can get this precise data. But from the data that we have out there, South Africa currently has about 68 or 70 data centers, right, which is actually the highest in the whole of Africa. And then we have when it coming back to production, electricity production, then we looking at Egypt, and then we're looking at Nigeria far behind, and then Libya, Tunisia, and all of that. So we see that when it comes to production, we have a long way to go in Africa. We cannot be just watching the other people playing along, doing a lot of things, getting lots of revenue, and we just want to be end users. That's actually how we've been in the past, but this is a time where we can actually go beyond that and then actually participate and then be ready for what's coming ahead in the future, because that's actually this is actually what we're going to be having in the future. The future is actually technology, but as a country or as a continent, we're not properly prepared yet. So we need to invest more in infrastructure so that we can actually really participate in all of this. And then we don't have to worry too much about where this is actually going to be coming from, the electricity that we need to generate and all of that, because we have globally the electricity from the chart I showed you earlier. The most of this power, they still come from conventional grid electricity, like coal, like oil, like natural gas, and all of that. So this is actually very important so that we can actually look at how we can exploit what we have. Well, I know maybe there are some people in this in this talk today who are proponents of, okay, greener energy, greener solutions. This is great. But in this case where we still have a long way to go, I think it's actually very hard for us to explore the resources that we have, so that we can actually maybe be at least do some catch up when it comes to these countries that are way ahead of us, because right now we can only play catch up. So we can actually do all of this by just exploiting what we have and exploring the solutions that we have locally. But it's still good where we can actually bring in more like a cocktail of solutions, like going into doing more research into batteries, going into maybe hydrogen solution, biofuels, and then we can use all of this to augment what we have currently, or what we're planning to achieve. So invariably, we're saying that data centers, they consume a considerable amount of power, and then there is the need for more infrastructure, like I've talked about. And then we can also diversify as well. Like, for example, when I was in Ireland, there was this huge amount going into exploring or using the wind turbine, because they're just by the Atlantic Ocean. So they're just trying to see how they can explore, how they can exploit this massive wind that we have on the Atlantic Ocean to get some wind turbine going, so that they can actually have more power. So we can actually like diversify, we can look at what we have around and see how we can improve on what we have currently. And of course, we need more research into, depending on the sphere that you are, we need more research to see how, for example, we can focus more on low consuming systems or low power consuming systems or devices. We can look at how we can optimize what we have. I'm aware that even the battery technology domain, we have a lot of research going on as to how we can expand. Some are even talking already how maybe to replace the lithium that we have, to replace maybe with some kind of a more reasonable solutions. So we have a lot of these things going on. So this is actually a call to action that we need to do more. So in summary, the increasing popularity of demanding applications such as cloud computing, video streaming, they've put enormous pressure on the network, on the technologies that we have today. But these we need to address, and then we should see them as opportunities. And then we've seen some solutions, and I focus more on the solution which pertains to my own specific field of expertise, showing you how we can actually scale up our business, and then how we can utilize this, maybe even as a consultant. This actually helps to generate even more employment. For example, I know people who have softwares like this, and then they serve as consultants to these big firms. They don't have the time sometimes to see how they can do some kind of research into solving certain problems they have. Then they have consultants who have the software, who can actually tell them, they can actually project, they can help them to analyze, they can help them to see some kind of aspects where they need to improve on, to optimize, right? So this actually provides opportunity for even small and large businesses to see how we can actually invest more, how we can bring in more entrepreneurs to see how to participate more in this huge wave of technology that's actually out there right now. And then we can also talk about research, especially those who are actually into those who are in academia here. So we need to do relevant research, research that's actually towards the benefit of the continent, right? We need to look at what the people are doing. We shouldn't focus too much on some kind of research that is a little bit obsolete. So we need to look into the future, see what's going to happen in the future, and see how we can prepare for that, rather than being reactionary, rather than reacting later on. We need to be proactive and do more research. So I think this is a good place to stop. Thank you, everyone. And then, yes. So
thank you, Dr. Muriwa.
Thank you.
If there are any questions, please post them into the question or the chat box. We have a few questions that have come through for you, Dr. Miwa. I think the first question maybe we can tackle this afternoon is a question from Andile. And the question is, what are data centers doing to manage and reduce escalating energy costs?
Oh, that's a good question. Yeah. So when it comes to data centers, for example, that's actually why I started with the case of this big in-ear computers that we used to have, where they used to consume lots of energy, and then after a while we had like good technology improvements when it comes to photonic integrated circuits, and then we're able to get to where we are today, where, like I mentioned, the Moore's law, where they said, okay, we're going to double the amount of transistors we're going to be having on integrated circuits for the next 10 years. And with that, we were able to get the computer. I'm sure you watching these or you participating in this using a computer, and this is actually how these things has gone down the line in recent years. And then talking about where we are today, data centers, they're still consuming lots of energy. So the one method is actually going hyperscale, where you're actually able to have one, instead of having different facilities all around, you have like a big data center, and then you are able to reduce the amount of overhead in this case. So that's actually how they were able to do all of this, like decrement in the power consumption. They call it the PEUs, right? And then it was actually getting lower because a lot of people, they are building more hyperscale data. That's actually some kind of small overhead when we look at the larger scheme of things. But the main thing here is actually the technologies that have been used. For example, I mentioned to you that servers, they consume more than 50% of the power needed in data centers. So in this case, that's actually why you have a lot of research going on in photonic integrated circuit. You have the silicon technology, silicon photonics right now, where they focus more on low power devices. For example, like the Coherent technology that I showed to you, that a lot of data centers are actually approaching now. They're actually working towards how they can actually develop transceivers where you have low power consumption. So in terms of the main devices or the main equipment that consume the most of this, more than half of this power consumption, we have these servers and these equipment, and we have lots of research going on to see how we can have low power consumption consuming devices or transceivers. We already have such, where you have lots of transceivers these days, where they actually getting like really they consuming like very low power. For example, there is the 100 gig Coherent pluggable out there, where the maximum power that it consumes is just 6 watts, right? 6 watts of power, which is actually not what we had before, way more than that. So we have this coming on, where you have this photonic circuit technology, where we're trying to get more and more from these devices with low power. And then, like I mentioned, the hyperscale helps you to have a bigger building. You have your equipment in one place instead of being scattered around. And with that, for the overhead, for example, you're able to plan more for the for redundancy, how they in just one building, and with that you cut some kind of overhead compared to building it in scattered places and then seeing how to connect all of this together. All of this consume lots of power, but now they're trying to bring these things together and have like bigger place, and then where you can control more of the power. So those are the two major places where we're talking about now. First, trying to build a bigger spaces. That's number one, so that you can cut off some overhead and all of that. And then you have the second, where which deals with the core of the matter, which is actually the IT equipment. So the IT equipment, we have lots of research going on these days, where we're trying to focus on low power consuming devices. So these are the two parts. But of course, as you solving one problem, another one arises. For example, we have this this rave about artificial intelligence. Because of that, you have data centers deploying lots of GPUs, and then GPUs, they consume higher power currently. So that's actually where you see this kind of canceling, this kind of cancellation here, where you're improving in one bit, but in another bit you're trying to bring in some other solutions that will actually increase the power. So, but of course, as we go, if we have this conversation, for example, in 10 years time, we see that we would have come a long way, because it's a good research out there where a lot of people, they're talking about devices where you consume very low power, and that's actually what a lot of research is actually focusing on these days. Thank you. I don't know if that answers your question.
Okay, yeah, thank you, Doctor, for that. We've got two more questions, and maybe just a reminder to all attendees that we have two handouts that you may download, the Academy brochure and our What Now October edition, the What Now magazine. So please look out for that and download that. Our next question, Dr. Miwa, is from Walter. And Walter says, thank you for the presentation. It's a great presentation. And he'd like to know more about power and cooling needs in terms of which areas and provinces would be ideal to build, taking into consideration the use of reliable renewable energy in South Africa. Now, I'm not really sure where you are positioned or where you're based, but the question is in terms of maybe in terms of the region, where would you suggest would be the best option in South Africa? And would you suggest Northern Cape as being a suitable area?
Oh, okay. Thanks for this question. But so maybe I'm not the best person to answer this question. So I'm actually located in the US. So I'm not, I spent a number of years in South Africa, but I cannot speak specifically to the places where you have, where you can see as a good place to locate this. But for example, in the USA, I can give you an example. Most of the data centers that we have, more than 50% of these data centers, they're located in Virginia. So with that, you're able to ask a follow-up question like, why Virginia? So number one, the place is a place where you need to talk about some kind of you need to put some considerations in place. For example, is there a place that is that has this propensity to natural disaster? So Virginia is not like this. You need a place that has some kind of nearness to that has this opportunity to have a lot of water, for example, maybe for cooling and all of that. So where is that province where you have access to a lot of water? I think from little understanding I have about South Africa, I'm not sure it's going to be Cape Town in this case. And then you look at, okay, what about the energy infrastructure? For example, how are they going to affect the people there? What's the population size? Is there a place that is highly congested already? For example, here, like again, referring to Virginia here, that houses more than 50% of our data centers, there is the Dominion power here. And this Dominion power in Virginia, that station alone, the data centers in Virginia, they consume 20% of whatever this power station generates. That's a huge amount there. So you're looking at a nearness to places like this, like, okay, which province is the province where you have closeness to some kind of power infrastructure? Where are you planning to build, or where do you have a high chance of building more infrastructure in the future? And then you look at the land and environmental factors as well. Where are places where are you considering a place where you have high propensity to natural disaster? You don't want all of these hurricanes and all of that. So those are the things that you put in, you consider before you can now talk about, okay, this is actually a really suitable place for us to locate maybe our data centers and to help us in terms of this cooling and power problem. Yeah.
Okay, thank you. Thank you. I think that answers the question. We have another question from Janet Gillespie, and she mentions that she's a bit surprised not to see Iceland on the list. Not as much energy is needed for cooling and lots of sustainable energy. And so the question is the limiting factor their distance from everywhere else? Or what would you suggest could be the possible limiting factor?
Limiting factor in terms of the power being consumed, or I didn't get the question.
Okay, so she says that she's surprised not to see Iceland on the list from your list of countries and states that have data centers. And so she's alluding to the fact that there's not as much energy is needed for cooling in that region, and there's lots of sustainable energy there. So what could be a possible limiting factor to them not having data centers?
Now I get it now. So in the list, we're just talking about the numbers. So if for example, if the list were to be longer, the list was to be longer than that, maybe Iceland is going to come up in at some point. But of course, you look at the closeness. One of the limiting factors, you look at number one, you look at the viability of the market there, how much they can invest. So for example, you have this competition between China and the US. So they're actually putting a lot of money into hosting these data centers. And then most of these giants, they're actually from these countries. For example, even the Equinix, which is actually here, they're actually having a number of growing data centers in Africa already. So what's the willingness to invest in data centers? That's actually number one. But number two, which is actually more important, was the future viability. For example, you have the data center, and then are you able to link them very quickly to the rest of the world? So for example, Iceland is actually slightly up. I think it's located slightly away from some major continent, for example, places where you have higher consumption. I'm not sure about this, but in the end, it's all about doing your feasibility studies, looking at the market that you're targeting, and also seeing how you can actually exploit that market. For example, the population of Iceland actually counts as well. Maybe what they have now is actually suitable for their current population, and then they're not looking to maybe push out there. For example, the more than 5,000 data centers that the US is building, of course, is not for the US alone. So they're targeting other markets as well. So how much of that do we have in Iceland? Are they targeting other markets? Do they want to target other markets? Do they want to see it as a core policy of the government or as a major source of revenue as a country? So those are the kind of questions that maybe their policymakers they answered, and then they're able to say that, okay, well, maybe it's not something that we need to invest in currently, but maybe in the future they're going to have like more and more data centers coming up, like for example in the US here or in Germany, where they have a number of data centers as well, and also China and all of the rest, like the rest of the world. Yeah.
Okay, yeah, thank you for that. I'm just going to take the last question this afternoon, and the question's from Raja Gangia. Thank you for the informative presentation. With liquid-cooled chips for AI and ML, what is the impact in terms of energy consumption when compared to traditional air-cooled data centers?
Oh, okay. So this is an interesting question. So this is actually not my field. I'm not so much into that aspect, but so maybe I might not be able to give you the kind of answer that you want. But of course, you need to for the differences. I think it has to do with some kind of efficiency, which one actually has better efficiency than the other. So maybe these are the considerations, but unfortunately, this is actually not my area of expertise. Yeah.
Thank you, Doctor. Thank you very much. I think definitely very informative talk and interesting conversations this afternoon. Definitely energy security plays a huge role in attracting investments into Africa and towards building data centers. I think we also need to reduce our reliance on both the East and the West. And there's a lot of room for development here in Africa. Thank you very much for your talk this afternoon. And I'd just like to remind our attendees to download the handouts. And we have our annual award ceremony at KZN this year. We will be hosting it on the 30th of November. So those of you that are interested in attending, please look out. Communication has been emailed through to you. And if you're interested in attending, please RSVP to our email address at the kznc@saie.org.za. Thank you very much. Good evening and a very good evening to the rest of you. I'll hand back over to you, Minx.
Thank you, Crystal, and thank you to Dr. Walua for your presentation. It was really informative. Ladies and gentlemen, which I didn't mention this morning earlier in this webinar, I will be applying for CPD credits for this webinar. So please look out for your attendance certificate, which will be circulated within the next 6 weeks. It all depends on how fast EXA can give us that number. But thank you for joining us tonight. Please look out in our SAIEE communications for upcoming webinars, and we bid you a very good evening. Goodbye.